Hello there, students. Have you ever wondered why hurricanes and cyclones always spin in a predictable direction? Or maybe you've just heard about this Coriolis force and want to understand where it comes from. Perhaps you've sat on a merry-go-round and tried to throw a ball to a friend on the other side while it's spinning, and had the ball take this crazy turn. What's up with that? In this video, I'll show you where this Coriolis force comes from and how you can experience it for yourself. First, let's draw two coordinate systems, one labeled with x0, y0, and z0. This is our inertial frame, meaning it is fixed in space and not accelerating and thus not rotating. Our second coordinate system will be labeled with x, y, and z, and is our non-inertial frame, or more commonly referred to as the body frame in blue. We'll also consider this generic vector v, pointing to somewhere in space. The vector and both coordinate systems share the same origin O. We can write the components of vector v in the inertial frame by expanding the components of the vector into the appropriate basis vectors. The general basis vectors are e hat sub naught I. Written out, they look like this. We obtain each vector component by projecting the vector onto each basis vector, like this. We can also write vector v in the body frame by expanding the components of the vector in a similar way, except this time using the body frame basis vectors e hat sub I. If the vector v changes or moves over time, then in the inertial frame, e hat sub naught don't change over time or move because that coordinate system is fixed in the inertial frame. This means the time derivative of e hat sub naught are all equal to 0 in the inertial frame. If we wanted to expand the time derivative of vector v in the inertial frame, we can look at the time derivative of its representation in the inertial frame basis vectors, e hat sub naught. The product rule for derivatives gives us two separate terms, but as we've just figured out, the second term is 0 because it's all about the change in the basis vectors. This leaves us with exactly what you'd have guessed. The time derivative of vector v in the inertial frame is just the time derivative of vector v's components in the same coordinate basis vectors. What happens when we want to know the time derivative of the vector v in the inertial frame, but using the basis vectors of the body frame? This time, because the body frame basis vectors e hat are not fixed in the inertial frame, their time derivative is not 0. Leaving us with two terms. The first term is simply the time derivative of vector v in the body frame. Now that we've got two expressions for the time derivative of this vector in the inertial frame, one using the inertial frame basis vectors and the other using the body frame, let's consider rotating the body frame a small amount for an infinitesimal rotation. When we rotate the coordinate system, some or all of the basis vectors will change. For this example, let's just consider a small rotation about the z-axis. The new basis vector at a time t plus an infinitesimal time later dt will be equal to the initial position, e hat sub I of t, plus some small deviation to the vector d hat sub I. Our body frame coordinate system is orthonormal, meaning all of the basis vectors are perpendicular to each other. Therefore, the dot product between any two of these basis vectors is the Kronecker delta. This just means the dot product is equal to 1 if the indices I and j are the same, and equal to 0 if they are not the same. As we can see in the diagram, the vector that represents the small deviation to the basis vector d hat is perpendicular to the vector itself, e hat. We can exploit the fact that the dot product between these two vectors is 0. First, let's expand this infinitesimal vector d hat into its infinitesimal vector coefficients along the body frame basis vectors e hat. We will use d omega ij for these infinitesimal vector coefficients. For these coefficients, if I and j are the same, then the entire coefficient is equal to 0. We'll see why in just a second. Using the orthonormality of the basis vectors e hat and the definition of the infinitesimal vector d e hat, we can take the dot product of e hat j with d e hat I. This coefficient, d omega ij, is equal to e hat j dotted with d e hat I. From this result, we can see that if we wanted to know the value of d omega ii is equal to e hat I dotted with d e hat I. We made the geometrical argument earlier that these two vectors are always perpendicular, and are thus zero, giving us this result. If we look back at the orthonormality of the body frame basis vectors, and take the differential of both sides, we can see that there is a relationship here between the infinitesimal coefficients. Namely, if you switch the order of the indices, I and j, you pick up a negative sign. This imposes a constraint on the number of independent terms, limiting us to 3 coefficients. We can choose to define them as such. Returning to the definition we have for the infinitesimal vector d hat, we can choose a value for I and then expand the summation. In this case, for I equals 1, we have d hat 1 equals d omega 3 e hat 2 minus d omega 2 e hat 3. While that previous result might look strange, it's actually just the result from a cross product between the vector d omega, defined in the body frame coordinates as d omega 1 e hat 1, plus d omega 2 e hat 2, plus d omega 3 e hat 3, crossed with the unit vector e hat 1. Let's see if we can use this to get the same result from just a moment ago. And there it is. Perfect. Now we can say that more generally, the vector d hat I is equal to the vector d omega crossed with e hat I. Let's consider a rotation about the e hat 1 axis. Then our vector d omega has only one value, d omega 1, along the e hat 1 basis vector. Then dE1 is equal to 0 due to a property of cross products. This should have been expected though, since the axis that we're rotating around shouldn't be moving in space, which is what dE hat 1 represents. Let's look at dE hat 2 now. Here we get a non-zero answer, and similarly for dE hat 3. If you wanted to check that dE hat 1 is really 0, you can plug it into the matrix and perform the cross product, and find that it is 0, as expected from above. With the general form of dE hat I, we can get another result from a slight manipulation. If we multiply both sides by dt over dt, we can define lowercase vector omega as vector d omega over dt, which is the instantaneous angular velocity of the rotating frame. Returning now back to one of our first equations, the time derivative of vector v, with our most recent equation, we can rewrite this summation term to include the vector omega. Then, from the definition of vector v expanded in the body frame coordinates e hat, we can condense the summation into just vector v, simplifying our equation into this form. When we started this derivation exercise, we had two coordinate systems, the body frame e hat I and the inertial frame e hat not I, and a position vector v. We found this resulting equation. It says that the time derivative of vector v in the inertial frame is equal to the time derivative of vector v in the body frame plus a term to account for the rotation of the body frame. This has the form of an operator acting on vector v. If we remove vector v from the equation, we see that the operator looks like this. When we apply this operator to the vector, we get the original equation back. Because this is an operator that acts on vectors, and the time derivative of vector v is itself a vector, we can apply this operator again. It looks super messy, but here we go. After distributing all of the derivatives and cross products, we're left with this equation. As a quick aside, if we applied this operator to the vector omega, we'd get this result. Again, due to the properties of cross products, we get a cancellation. What this does is show that the time derivative of the vector omega in the inertial frame is equal to the time derivative of the vector omega in the body frame. Since these quantities are the same, regardless of the frame, we can drop the label which tells us what frame it's in. Doing that, we have this final equation. If vector v started out as a position vector, then its second time derivative is an acceleration. To turn this acceleration into a force, since we always hear about the Coriolis force and not the Coriolis acceleration, we can just multiply a mass term throughout our equation. We rearrange the terms so that we're just looking at what the force measured in the body frame is equal to. This isn't a complete equation, however, since we only considered infinitesimal rotations and we neglected infinitesimal translations. To make it a complete equation, we add a linear acceleration term, the derivation of which I'll save for another video if needed. For now, though, we see what we call the Coriolis force, equal to -2 times the mass, vector omega, crossed with the time derivative of vector v in the body frame. We also see the other common fictitious force, the centrifugal force. Now, with all of that derived and sorted out, we can apply it to some example problems and see how it answers the questions about hurricanes and merry-go-rounds. For the first example, let's consider a cannon sitting at the North Pole pointing due south. In the body frame, the one that is fixed to the Earth, as if you were standing right next to the cannon, when the cannon goes off, you would expect the ball to travel in a straight line due south, landing somewhere in India, I guess. But in reality, when the cannon goes off, the projectile curves off to the west, landing safely in the water. This is what it would look like in the body frame fixed to the Earth. And this is what it would look like in the inertial frame. As you can see, in the inertial frame, it does in fact travel in a straight line. The Earth is just rotating underneath it. With the Earth spinning along the z-axis, the vector omega looks like this. And the position of the cannonball as measured with vector r, which has a velocity of vector r dot, the dot signifying a single time derivative of vector r, looks like this. Here, our x-axis is lined up pointing due south. Plugging in our vectors and completing the cross product, we get the resulting Coriolis force, vector F core, as equal to -2 times the mass of the cannonball times the velocity of rotation omega times the initial velocity of the cannonball r dot in the y-hat direction. Because of the negative sign, the actual direction is negative y-hat, which is west. Exactly as where we see the cannonball landing in the inertial frame, in the water somewhere west. The merry-go-round example is essentially the exact same problem as the cannonball we just solved, but let's take a look. Similar to the cannonball example, from the body frame attached to the rotating merry-go-round, you'd expect to be able to throw a ball to a friend sitting across from you in a straight line like this. But in reality, the ball will curve off to the side, away from your friend. If we learned anything from the cannonball exercise, we know what's happening here already. The ball is actually moving in a straight line if we look at it from the inertial frame. The merry-go-round is just rotating underneath it, like this. We can set the problem up in a similar way, with the z-axis pointing up as the axis of rotation. And we throw the ball due south. In my choice of coordinate system, due south is negative y-hat. Following the equation through, we see the exact same result as before. The ball will feel the effects of the Coriolis force and be accelerated westward, away from the original target. This is also one of the main reasons a hurricane or cyclone gets its spin direction. In the northern hemisphere, as particles are pulled southward, closer to the equator, they are seemingly deflected westward. Conversely, as particles are pulled from the south to the north, they are deflected eastward. This net effect is a counterclockwise rotation of the entire system. The opposite deflections happen in the southern hemisphere, resulting in a clockwise rotation. Thank you for watching and learning a little bit about physics. If you have any questions or video requests, drop a comment below or head over to my Facebook page in the video description.